let's look at some basics, some building blocks of area. Everything we do involving area is going to be built off of this idea of what the area of a square is. And hopefully what you call the area of a square is simply just area of a square is simply just its side squared. Multiply side by side. The area is one dimension multiplied by a perpendicular dimension. In this case, length times width. Whatever. We're going to build everything that we have an area off of area of squares. So everything we do can eventually be broken down into tiny, tiny little squares. Sometimes we have to get infinitesimally small, really small, but kind of where we're headed. Okay. Areas behave in the same fashion that segments do, that angles do, and that two areas are congruent. We can have areas being congruent, meaning that areas have the same measure for the area. Two areas with the same value, their measure.
Wait, what's the word after the value?
For there, 2 words. For there. Just like two segments are congruent if they have the same length, that's how we measure a segment. Two angles are congruent if they have the same angle measure. Two areas are the same if they have the same area measure. So in square unit, in square inches, and square yards, and square miles, square centimeters. They're the same and they're congruent. And last but not least, addition, we can add areas. So just like we have segment addition postulate, we have arc length addition postulate from last chapter. You have angle addition postulate. The same thing can be said for areas. You can add an area is equal to the sum of its non-overlapping parts. Take all the parts that don't overlap, that just fill the area, you add those little parts together, you get the area itself. So area additions, just like area addition postulate. Kind of those three basics properties of area that we're building from. From these we have two review formulas for shapes that we've seen in the past, common shapes. For example, a rectangle. For any rectangle of width W and length L, its area is width times its length. We'll multiply those two things together. This formula is built on the idea that if we divide these into a bunch of squares, then we'll have W squares going across. We'll have W squares going across and L squares above. Add all those individual pieces together, and the sum is the same as if we just multiply the length and the width. Area of a triangle is built off of the area of a rectangle. Area of a triangle, and I'll denote area of a triangle by A for area, and then kind of a what's called a subscript, and I'll draw a little triangle for a triangle. Area of a triangle. Hopefully you recall. Half of the triangle's base times its height. For any old triangle, we'll measure base and height. Base being just what any one side of your triangle, and the height being the length of the altitude from the vertex down to that side that we're calling the base. So for some triangles, it's easier to measure to choose a base and a height that's convenient. That is going to be that we can actually measure one of the bases and the heights off of it. Do you have any questions about this so far? This is hopefully a good, solid base of review. Anyone unfamiliar with the area formula for a triangle? Okay. We're going to look at some other figures that we've already studied, namely those quadrilaterals that we've studied quite a bit. We'll look at parallelograms. We looked pretty in-depthly at parallelograms before. We'll look at their areas now. We also looked at trapezoids and kites and rhombi. We're going to look at those tomorrow. Okay? But from that, in order to find formulas for the area or just think about them intelligently, we're going to build, how we're going to find areas of other figures, we're going to build formulas from we're going to build our formulas. Everything that we do in this chapter is going to come from those basis things. So the formula for a square, the formula for a rectangle, the formula for a triangle. We're going to build our new formulas, say, for parallelogram today, off of our knowledge of those two ideas. Specifically, let's look at a parallelogram. So, let's see, let's draw one. Can I draw one? Probably not. That is not parallel. That's a lot closer. Let's start with a parallelogram. I want to find the area of this thing. In order to find the area of this parallelogram, it could really help define the area. If we could break this figure into, say, rectangles or squares, then we could calculate the areas of those things. And that could help us. And then we could just add those areas together, and that should tell us what the area of my new figure is. In general, I have a parallelogram here, and I don't know. What do we know about parallelograms? What are some properties of parallelograms that we already know off the top of our heads? Katie, what's one? Opposite sides are congruent. So I know that since I'm working with a parallelogram, I know that these two lengths are the same. I also know that those two are the same. Right? And opposite angles are congruent. So I know that that angle is the same as this one. I know that those two are the same. I'd like to redraw, I'd like to be able to take this picture, in this picture in general, and I'd like to be able to break it down into these things, either rectangles or triangles. Here's one thing I see. What if I do this? I'm going to take a line, and I'm going to start right here at one of the vertices, and I'm going to draw an altitude straight down at a right angle. I'm going to draw an altitude straight down. And notice what I created. A nice little right triangle. If I take this right triangle, and what if I take this right triangle and I cut it off of here? Let's see if I can do this. This could be interesting. Oh, hey, how about that? Take this right triangle. I'm going to fit it in right here. You can't do that in your paper yet. You probably can't. What have I just made? Perfect. A rectangle. It must fit there. The reason it must is, well, this triangle, and if you were to draw another one right here, you'd get two congruent right triangles because we just said that those sides are the same. These angles must be congruent. How would we find what if this is a rectangle, then we should know its area is length times width. So what's like the length of, what we call, say, the length of this new rectangle that we just made? What side would correspond to, say, like a length of the width? Like what sides on here would we want to know in order to calculate the area of this thing? Brett, what's one?
Both. One's on the side. Kind of. I don't know. They don't have numbers.
Like this? Okay, so I don't have any numbers. But I do want like the top, and I'd like...
Or, yeah.
Like those?
Well, you mean the whole side.
What did that correspond to? This side we didn't cut anything off of. This side was just the length of one of the original bases of this parallelogram. So for our rectangle, the length of this rectangle corresponds to a length of one of the bases of this parallelogram. The width of this rectangle, well, that's not the other side, unfortunately. The other side is this hypotenuse. But it is the distance between these two bases. It's the altitude that we drew in. So the width is just the height. We call this the height of a parallelogram, which is the distance between the two sides. The area of this would you believe me that the area of this rectangle is exactly the same as the area of that original parallelogram? All I did was cut this chunk off and move it over here. So the area of this parallelogram is basically the same. The formula is going to be basically the same as the area of a rectangle. Only the sides I'm looking at are one of the bases and the distance between the two bases. The perpendicular distance between the two. Or the backside, the area of a parallelogram. If I have, say, a base and a vertical distance between the two, we'll call h for height, then the area of a parallelogram is equal to its base times its height. So if I go through it, I need to find, say, the areas of several figures. I have tools right now. I have our squares. We have rectangles. We have triangles, and now parallelograms. Okay. So if I ask you to find some areas in here, some strategies we might want to use would be to try to break these figures down into at least one of those four figures and calculate those areas, and then we can add them together. So if I give you some parallelograms, see our area first, we'll see. I have a side and the distance between the two opposite sides. The area of this parallelogram should be 11. This is my B, and this is my height. Then the area should be, what, 11 times 9. So it's 99. Do I have units? I don't have any units associated with this. No units.
So do we have to write units squared for everything?
I would like you to. Please, one thing I would not want to see, there's a difference between 99 units squared and 99 squared. Those are different things. It's the same thing, 99 and multiply by itself. This is telling me that this number 99 is a unit of area. Okay, make sure we have whatever. If I don't give you an area, let's kind of get in the frame of mind of labeling it as just whatever units I attach to it squared. We got unit squared, you got u squared. This is something to denote that what this number we're talking about has a meaning, and its meaning is an area. Okay. I'm going to trust that you can do this. Is this a leap of faith that you can do the second one and quite possibly the third one on your own? I'm going to skip these two. I'm gonna do D with you, and then I'll leave the last two as practice problems that I'll come around and check. We'll go over it in just a minute. I'm gonna skip these two. These are just base applications of the formula, nothing new. Next one here in D, this is not a parallelogram. It's not a rectangle. It's not a triangle. So we don't have a formula yet to deal with this. In fact, this is exactly a trapezoid, which we'll get a formula tomorrow for. But if you forgot this trapezoid formula, or you don't know it yet, we can actually break this down into some figures that we already know. Namely, how would we break this guy into, say, a rectangle? Let's break this into a rectangle and a triangle.
What is that? A little triangle.
Okay. By breaking this into two figures, let's now label things that we know. So, for example, this distance better be the same as this distance. What's this little piece right here?
2.
Better be 2 because if we make a rectangle, now we should have 10 and a 2 because the whole thing was 12. So now let's find the area of, I'll denote areas with like Roman numerals. So I want to find the area of our first thing. Let's find the area of this triangle. And then the area of the whole figure better be whatever the first area is plus whatever the second area is. Namely, 6 times 12, which is what, 72, plus half of 12, which is 6. 72. 6 times 2 is 12. Half of 12 is 6. Area of a triangle is 1/2 base times height. Base, height.
No, because you did 6 times 12.
Oh, sorry, 6 times 10. You're absolutely right. Yeah, absolutely right. That didn't make sense to my idea. 6 times 10, yes. 6 times 10, yes. Area of the rectangle. 6 times 10 is 60, plus half of 12, which is 6. 60 plus 6 is, the area of this figure better be exactly 66 square units. For those of you who don't have the notes printed, here's the next two figures. Let's copy these figures down, please. I'll scroll back up to get those basic ones so you get the little bit of practice that we skipped. If you feel confident with those first couple, you don't have to worry about it. But these two are certainly ones that I want you to practice. This one, the last one, F, is a little bit more challenging than it might first appear. You have to do a little bit. You're not going to just be able to plug directly in the formula. You don't have the information right off the top of your head. Okay? You have to find a missing piece in here in order to calculate the actual area. Okay? So let's get on those. So some of you I saw tried some various methods for finding the area. One method I thought that might have potential and it might actually work. You could probably maybe go back and check versus the method we eventually did versus the one you started. Because I'm letting you guys that want to make the big rectangle. Yeah. Maybe your method actually would work, but I know the one we ended up at certainly just breaks up this figure into its pieces. Yeah. Dividing it down the middle creates two trapezoids, which doesn't really help us because we don't know the area formula for a trapezoid yet. But if we divide it, say, across the top here, we get yourself a rectangle and a triangle. And if you can add those two pieces together, we can get this overall area. Or the area of area 1 here is got to be 6 times 18. Area 1 is just 6 times 18, which, someone that did it, can you remind me what 6 times 18 is? 108. Area 2 was this triangle. The area of a triangle is its base, half its base times its height. Well, the height of this triangle is just 6. And the base then, or the side this altitude intersects, is this leg, or this side of the rectangle, which is 18. So half times 6 times 18 is what, 3 times 18, which is maybe 54. Therefore, the area of this is what, 162 square units. Our triangle over here might look inconspicuous, but you don't quite have enough information right off the bat because you don't know the height of this thing. We know this leg, or this side, if it's a right triangle called a leg, we know this side is 10, but we don't know what the height is. So we got to find it. We do know that this whole base could be 30 plus 6 is 36, but we don't know the height. Well, to find the height, a lot of you were able to notice we broke this down into looking at just this little right triangle. And since it's a right triangle, we know that the Pythagorean theorem holds. And you could say, how about 6 squared plus the height squared is equal to the hypotenuse squared, which is 10. 36 plus a squared is 100. A squared is 64. The height is 8. So the area of this big triangle is 1/2 of, one way to do it, 1/2 times 36 times 8, which is exactly 144 square units.
Wait, what's that after the equals? Oh, that's 100. Just kidding. We don't have sure.
Good job.
The area of that triangle is 144 square units. Excuse me. You could also, once you could break this into 2 triangles and do one triangle with base of 30 and height of 8, and a second triangle with base of 6 and height of 8. And I claim that if you add those 2 areas together, you'll end up again with 144 square units if you did it that way.
Yes.
Tomorrow we're going to add to our little repertoire of areas. In particular, we're going to look at specifically trapezoids and kites and rhombi. Okay?